And welcome to our bonus features segment. We're seeing chaos in Earth's electron bands once again here. Some nighttime GPS errors likely to be happening. It's the total electron content forecast. The free electrons in between your GPS handset and you at the surface. When that GPS satellite must communicate through a lot of electrons, it creates errors up to thousands of miles. And this graphic shows you the most likely locations for those GPS errors. Just turn on your Wi-Fi location accuracy to decrease the likelihood that you will be off by a massive distance, especially around the equator at noon. Yes, you can use Wi-Fi. IP addresses have known locations, which can increase the accuracy of your navigation. So here's just a diagram showing distances in miles. We show it daily to keep people understanding what it is we're looking at. There are some electrons in the plasmasphere, which is this space right here. Right in this area, that's the plasmasphere. And here's the inner Van Allen belt. That's where most of those free electrons are located. Let's continue on to look at charging hazards. We've got some internal charging hazards here. These are caused by the higher energy type electrons, the higher voltage. Surface charging caused by the lower energy type electrons. So some significant surface charging and internal charging hazards here. Don't be surprised to see some communications failures as a result of that. Here's the 1-year chart of the relativistic electrons. And here is the 3-day chart from the GOES 16 and 17 measurements. These satellites are measuring the electron flux at the F flare from their geosynchronous orbit. And we're going to show you the F flare in a minute. We got into warning levels once again here. So high levels of electron flux and a bit of chaos. Some GPS errors at night. Here's the forecast, expecting even higher levels here. I have no reason to argue with the NOAA forecast. Let's continue on to look at the ionosphere located at about 300 kilometers of altitude. Here's the F flare, one slice. Shown in vibrational frequency. Megahertz, millions of vibrations per second is what a megahertz is. We used to measure computer calculation speed in megahertz until we got to gigahertz, billions of vibrations per second. This is millions. And we're going to show you the anomalygram as well to put it in context. Here's the anomalygram showing anomaly in megahertz from the 30-day median. So we're showing a bit of a long-scale anomalygram here. It helps to put this in context if you're not familiar with looking at the ionosphere. It's courtesy of Australian Government Bureau of Meteorology. Shout out to Kimberly for making this apparent. So quite a bit of anomalies here. We're going to bring up the latest image. There's the ionogram from 1245 Universal Time, and there is the anomalygram from 1245 Universal Time. Here come additional bonus features. But first, I'd like to welcome each and every one of you to the Neo Renaissance. Congratulations on realizing the channel exists. Please visit our links, support the channel via smashamash.com. If you want to read about what we're up to, head to the homepage, have a read. Become a member of the Smash team if you enjoy the content and prefer to see it continue to exist and remain publicly visible. Smashamash.com/Smash team is our answer and replacement for Patreon. It's a subscription website service. So log in. What's your favorite social media? Now we're on Getter. We don't see hardly any engagement there. I think it's rather silly, actually. And shout out to Smash staff for posting our content every day on all kinds of social media. So we're on Twitter, we're on Facebook. Let us know what your favorite social media is in the comments. And we're probably already on there. So yeah, let us know. Leave us a comment. And we'll be more than happy to set up an account there, maybe. But most likely we're already on your favorite social media. Please press like, subscribe, and share, as the algorithms do not seem to be particularly helpful in getting our content onto screen. So here's our next bonus feature. This is the Cerro Tololo ground-based solar observatory here. Part of the National Sunspot Observatory. Great view of some filaments here in hydrogen alpha. Some filaments here as well. So we may see the situation reaching optimal here for coronal mass ejection forecasting. If you're wondering what happened to our coronal mass ejection forecasting, we've stopped doing it because if it don't make dollars, it don't make sense. Here are the sunspots. There you can see some setting sunspots there in the northwestern limb. Here's 2940. It's still capable of producing significant flares. Here's 2941, which is the most interesting sunspot now on the closest star. That one is still beta class as well. Again, we just showed some filaments associated with that. Here are the fields. It's hanging on to its beta classification. There's 2941, quite magnetically complex, more than capable of producing major flares. There's 2940, still significant. And this one's setting over here as a beta class sunspot as well. There's the zoomed out, freshly refreshed colorized magnetogram. We got some more solar imagery for you to close out our bonus features segment. Little prominence here coming out of this active region. And we're still watching the activity of this filament. It looks like most of the plasma has collapsed back down onto the lower corona, I'll say. A great wavelength to view solar flares is 94 angstroms. It's one of the many wavelengths from the SDO that we follow. It's ionized iron, and it takes more images per minute. It's specifically designed to watch solar flares, as well as 131 angstroms. Our first daily space weather video of the day showed 304 angstroms, some close-ups. Make sure you check that out if you haven't. We'll close out today's bonus features with this spectacular view, ionized helium from the Solar Dynamics Observatory. Thanks for tuning in, folks. Congratulations on realizing the channel exists. And may that solar wind be at your back.